once we can set up a heat conservation equation, we're in a position to look at an experiment that is going to determine how much energy a chemical change releases or absorbs. For example, suppose I've got an acid-base reaction. Here I've got some sodium hydroxide that's going to react with some HCl. And we know how to complete that equation. And there, and it's balanced. And I want to find out how much energy is this neutralization reaction that's going to occur in this cup going to produce. Now I've got a cup, and it has a known heat capacity. That's the big C there. And I've got an amount of acid, and I know the volume of the acid and its concentration. And I also know its initial temperature. It's at 25.1 degrees Celsius. And here I've got another cup that's got 50 milliliters of 0.100 molar NaOH. And it's at the same temperature as the acid. So they both have the same temperature. Now when I mix them, something happens. A reaction occurs, and it raises the temperature of the solution inside the cup. And I'm going to assume that when I measure that final temperature, that's the final temperature not just of the solution in there, but also the cup. Now what I want to know is how much energy is absorbed or released in this reaction. All right, step one is a calorimetry problem because we're trying to relate heats with temperature changes. I am going to look at the three components of the system. Now you might be tempted to say the three components are the base, the acid, and the cup, because that's what I've given you information about. But, like we talked about in the last video, this would be the wrong approach because it's not the base alone that absorbs or releases heat. It's not the acid alone that absorbs or releases heat. It's the reaction that occurs between them. And the solution that the reaction occurs in is absorbing the heat. So these two components of the reaction are wrong. This is not the right heat conservation equation. It should look like there's a reaction, RxN is my abbreviation for that, that produces the heat. There is a solution, SOLN is my abbreviation for that absorbs some heat, and then the cup is going to absorb some heat too. So that is my correct heat conservation equation. The second thing I want to do is replace the Q's. Now I can't replace this one because this is my unknown. This is what I'm trying to find. How much heat is absorbed or released by the reaction. But I can replace this one. For the solution, I know the mass of the solution when I mix these two. Now, do I really know the mass? I told you 50 milliliters and 50 milliliters here. If I knew the density, I could convert those into grams. The density of water is about 1 gram per milliliter, so I can approximate the mass of this solution as 50 grams. And I can approximate the mass of this solution as about 50 grams too. So I'm going to do that. And I'm going to say I know the mass of the solution. And the specific heat of the solution, I didn't give you that either, but I can approximate that as well. I can say these solutions are mostly water, so I can use the specific heat capacity of water in here, times the temperature change. Now let's replace all these pieces. The total mass of the solution when I mix them is going to be 50 plus 50. It's going to be 100. The specific heat is going to be the same as for water. So I can look that up for water. And then the temperature change is going to be the final temperature, which was 27.4, minus the initial temperature, which was, in both cases, 25.1. And if I do the math there, what is that? 2.3 degrees C. And it's positive, and that means that the temperature rose. We had talked about that in the last worksheet. The sign on delta T is positive if the temperature went up, and it's negative if the temperature went down. Okay, so I multiply 100 times 4.18 times 2.3, and what am I going to get? Let's see, 100 times 4.184 times 2.3 gives me 962. And I'm not going to worry about significant figures right now. Well, we can worry about that later. And joules are the units, because look, grams and grams cancel, degrees Celsius and degrees Celsius cancel, and I'm left with joules. This is what Q solution is. Okay, now let's replace Q cup with something that has delta T's in, because step 2 in a calorimetry problem is replace the Q's with things that have delta T. Now here I know the heat capacity of this, so I can replace it like this. Now I'm going to assume the temperature change is the same as, the temperature change of the cup is the same as the temperature change for the solution inside of it. And I know the heat capacity that's given, and I could have found that in a whole separate experiment. So I multiply these two things together, I'm going to get, 400 point something. Let's get a number for it. I'm going to get 460.2 joules. All right, so I have a number for this and a number for that now. Now how can I get Q reaction? Simple now. I can solve the heat conservation equation for Q reaction. Q reaction, that's the third step, is solve for your unknown. Q reaction is going to be minus Q solution minus Q cup, which we've just determined is going to be minus 962.3 minus 460.2. Let's get a number on for that. Minus 1422.5. Okay, joules. Now, this means the minus sign that we get on the end means that 1422.5 joules of heat are released. Now that makes sense that the Q reaction would come out to be a negative number, because if heat is being released, the contents of the cup will warm up, and they did. They went from 25.1 to 27.4 degrees. Now, how about significant figures? I mean, how many significant figures do I know this to? Really only 2, right? Because I only know my temperature change to 2 significant figures here. So, I really only know this out to the tens place here. So I'm only going to know this out to the tens place as well. So really I should say minus 1420 joules. And then I have 3 significant figures for that. Now for this one here too, I would also know this one only to 2 figures. So I'd only know it out to the tens place. So I would only know this out to the tens place as well. And that would be the proper way to round off my final answer. Now this is a big piece of the last problem that you've got on this worksheet. We've done almost all of that problem here. But there is another piece, and it has to do with the Q reaction here. Is this the best way for us to report the amount of heat that this reaction produces? Well, what if I changed the amount of base and the amount of acid that I had? If I had more acid and more base both, I'd be producing more heat, and this number could go up and down with the amount of reactant that I had. It would be nice if I had some sort of concentration independent way of reporting how much heat a reaction absorbs or releases. And that's what we're going to look at next. It's called the enthalpy of reaction, and it is the amount of heat that this reaction would have produced if I had 1 mole of this reacting with 1 mole of that.